Egunon Danori. Good morning. Buenos días a todos. Vamos a comenzar el cuarto Simposium Internacional Egurtek de Construcción, Arquitectura en Madera, organizado por el BEC y con el patrocinio del Gobierno vasco. Bueno, yo me llamo Ramón Ruiz Cuevas y es un honor para mí presentároslo porque reúne tres de mis pasiones: la madera, la arquitectura y la sostenibilidad. Antes de empezar con las ponencias, que es lo más interesante, voy a hacer un pequeño resumen para que os organicéis, para que sepáis cómo se va a programar este congreso a lo largo de este día y de mañana, pero vamos, yo voy a describir hoy el día de hoy. Ahora vamos a escuchar dos ponencias muy interesantes. Luego a las 11:30, de 11:30 aproximadamente, a 12:15, vamos a poder tomar un café en la zona expositiva de Egurtek, que está en el nivel 3. En el nivel 3, que es el nivel más bajo. Nosotros estamos ahora en el nivel 4. Es un poco follón lo de los niveles, pero en el pabellón Lusúa. Entonces, en este nivel 3 es donde están los espacios de las empresas expositoras. Hay más de 20 empresas muy interesantes. Luego también hay una exposición en formato A1 de los paneles del premio Egurtek. Bueno, podéis tomar un café, hay una zona de descanso, una zona wifi gratis y una zona para que estéis trabajando o descansando. Y también podéis, en esos momentos de café o de relax, recoger un prontuario informático de madera estructural que luego se presentará. Después volveremos aquí, ser puntuales, y a las 12:15 aproximadamente, o bueno, luego ya igual, según los tiempos de la mañana lo corregiremos, pero más o menos está programado que a las 12:15 será la tercera ponencia. Luego, a la 1, será la presentación oficial del prontuario informático de la madera estructural, que es una herramienta informática que sirve de ayuda en el proceso de cálculo y comprobación de elementos estructurales de madera. Está elaborada por el Área de Conocimiento de Ingeniería de la Construcción de la Universidad del País Vasco, con el patrocinio del Departamento de Medio Ambiente, Planificación Territorial, Agricultura y Pesca del Gobierno vasco. Y después ya acaba la sesión de la mañana, pero el BEC y la organización, en este espacio de 2 a 3:30 para comer, hay 3 opciones de comida con diversos precios, vamos. La primera sería en el restaurante Gastañaga, que está en el nivel 7 del centro de congresos, con un menú de 40 y tantos euros. La segunda sería en la cafetería Chairu, que está en el nivel 0, con un menú de 15 euros. Y la tercera es un sistema de comida rápido, con bocadillos de ibéricos, café, quesos, etcétera, que está en el nivel 1. Bueno, repito que nosotros estamos ahora en el nivel 4, el café es en el nivel 3. Bien, y bueno, luego después de comer, ya os lo recordaré después, ser puntuales, porque a las 3:30 empiezan las ponencias de la tarde. Bueno, antes de Marcel, y después de este momento más prosaico, para meternos un poco en situación, os quería leer un breve verso de una novela de José Luis San Pedro, que aunque es un trozo de novela, es muy poético. El olmo ya seco de la ermita debe su único verdor a la hiedra que le abraza, pero ella a su vez, solo gracias al viejo tronco, logra crecer hacia el sol. La madera y el verdor, la raíz y la sangre, el viejo y el niño avanzan compañeros como sobre un camino por ese tiempo que les está uniendo. Ambos, hombro con hombro, en extremos opuestos de la vida, mientras la luna se mueve acariciándoles entre el remoto girar de las estrellas. Bueno, aquí, no sé, resumes todo lo que es la madera viva, la madera muerta, este material fantástico que además crea una economía y que está unido a la vida y que, bueno, se escriben muchas poesías sobre los árboles y la madera. Bueno, ahora ya empezamos la primera presentación. Marcel Baumgartner, sorry for my bad pronunciation, es arquitecto por la ETH de Zúrich desde 2001 hasta 2003, trabaja en el estudio Berth and de Plas Architekten y desde entonces colabora en la propia escuela en la cátedra del profesor de Plas. Es director del proyecto del refugio del Monte Rosa, obra de Berth and de Plas. Y, bueno, el refugio del Monte Rosa, todos lo conoceréis, es un edificio magnífico, autosuficiente, que yo lo definiría como una roca desprendida de la montaña que se ha transformado en una lámpara maravillosa ahí en medio de los Alpes. Come on. Start, please.
To get a headphone. Could you please take down the lights here so that the images get the light off? Okay. 45 minutes. Huh? Buenos dias. Good morning, and thank you very much for this nice introduction, and thank you for inviting me to Bilbao to this Congress. I apologize for my limited English. I hope the translators will make out best of it. So I brought a lot of images that might explain much more than any words. I just go right into the project. So I would like to start with this image of the building site, which is in the south of Switzerland, and the construction site is right here. It's on about 2,830 meters above sea level, and it's at the bottom of some of the highest peaks we have in Switzerland, the Monte Rosa mountain. It's in the midst of a very beautiful, very sensitive natural landscape of glaciers, rock, and snow. The interest or the challenge for us was that this building site explains kind of like an ideal island situation. Actually, there is no street access, there is no running water system, there is no wastewater disposal, there is no electricity. So if you would like to build there, you have to create everything you need on your own, and everything you do will become visible. So this is an ideal island situation for a case study project. A case study project that is about building under extreme conditions and is about sustainability, question of energy efficiency. Here again, an overview of the situation. We are in the southern part of Switzerland, close to Italy, to the border of Italy, in the midst of some of the highest mountains. Here you see Zermatt, which is an internationally well-known tourist spot, highly urbanized, high infrastructure. And here you will find the Matterhorn, this famous mountain peak you will find on kind of every chocolate or whatever. And the building site, close to this rather dense and urbanized areas, just a few hours of walking, and then you're in the middle of nowhere in splendid isolation. In the midst of these glaciers, it sits right here. So mountain cabins do have a long tradition in Switzerland. So this is actually the first Monte Rosa hut built in 1889. So the Swiss Alpine Club takes care of about 150 mountain cabins like this. And the basic idea, it's not about the hotel, but it's rather about giving simple shelter, provide simple food, accommodation. So this project actually was initiated by the Swiss Alpine Club and the Swiss Federal Institute of Technology, the ETH Zurich, which is a technical university with a faculty of architecture. And we as architects, we thought that this case study would be very interesting to be developed with students, in the idea to have like education and practice coming or bringing together. So what we started up in 2003, actually a long time ago. We started to establish the Studio Monte Rosa, which is like a design class in the master studio of the ETH. And we worked with a group of students, a changing design team over a period of like 4 semesters on the basic concept and concept of this project. What you see here is the result after like 2 semesters of studies, where you get an impression of just a bunch of ideas, of strategies, how you could build under such extreme conditions. And these projects, or these kind of design approaches, they try to reflect all the extreme conditions. For example, how would you establish a structure on this in this rocky landscape? Or how would you bring your building material on site? Or how would you solve the problem, the issue of water and energy supply? And what are does these technical aspects or parameters, how do they influence the architecture? Because that's what was our main interest. It's not about the technological problem, but in the end it becomes physical, it becomes spatial, so it becomes architecture. One semester later, a lucky group of students, they came up with this vision, which is a virtual idea of this project, which somehow combined all the research we did before, brought it together, and put it into one very dense project. Before I go into like the architectural or the structural and constructive questions, I first have to talk about the building services, because as I mentioned before, it is not just about a nice architecture, it is about the interaction of technological questions and questions of architecture. So imagine being in the complete loneliness, and how would you solve the very fundamental issues to run a small house or a building or a small hotel. One of the main issues is about water supply, because when we think about energy saving, we first had to solve the water problem. Because in the old Monte Rosa hut, a lot of energy was spent to provide fresh water. That means during the year they melted snow to have fresh water. And this actually took most of the energy, which had to fly in by helicopter. So this is a very simple but a very helpful idea that we created like this huge reservoir, a cavern, like a rock cavern, that stores the amount of water we need for 1 year, to run the hut for 1 year. And this cavern is filled in summer when the snow is melting naturally, and then we fill up this cavern. The water is going down to the hut, is used for kitchen, for hygiene and so on. And an important part is this one here. We have this biological wastewater treatment, or the wastewater plant that allows us to first to recover or recycle about 1/3 of the water. Actually, water is a very, very valuable good on this site, and on the other hand, it allows us not to release any wastewater to the natural environment. So we only release clean water. So this is quite common, you might say, but the challenge was to build up a stable system in this island situation with no backup system at all. The power, electricity, is created with the power of sun. So we have a huge photovoltaic field on the building. And here, this is one of the most important piece or which had the most impact on the architecture, because it's one of the biggest like island photovoltaic we have in Switzerland. So that means it has a certain surface, it has a certain angle we had to put it on, and it provides quite an amount of power we store in this big battery park here. This provides energy for kitchen, lighting, building service, and so on. And there, for rather extreme situations or conditions, we have here a small cogeneration plant for backup supply of power and heat. Talking about heat, we also use the power of the sun. We have this quite a huge thermal collector that provides heat that is put into this storage here and provides warm or hot water for kitchen and so on, but also provides heat for the ventilation system, a ventilation system with a heat recovery. And here again, the backup system for extreme situation without sun for a couple of days or a few weeks. So, as you might have noticed, this is all quite well-known or you might say common technology that is well-known for years, since the 70s and so on. But what is the challenge, or was the challenge for us, to create a stable system that works on its own? And the challenge that the actual research is going on is about how you manage with those resources you create. You create some, or you use natural resources like photovoltaic, thermal collector. You have the wastewater plant, which takes a lot of energy. Therefore, it is kind of like a passive storage, like an energy storage. And you deal with these rather unreliable natural resources. And the question is, how would you run this system to get it stable, and so that we can avoid to use the backup system, which would create some CO2 emissions. So this is the actual research that is going on this very small but kind of ideal case study object. I'm not going into details, it would take quite an amount of time, but I would like to go back to the architectural consequences of this concept behind. So, talking about the concept, like the architectural concept, there's one way to explain would be the relation between the building and its situation or the surrounding landscape. So our goal was to make us as small as possible, that we do not spread out in this landscape, but rather we get compact as possible, to have the smallest footprint you can imagine. And we ended up with this like small but tower-like building that works like a milestone in the landscape, like a lighthouse. It kind of points out the virtual center of this tremendous landscape. So this is the point. This is actually the build project. This is the point where you go to or from where you would go to the mountains. So it's the center of the landscape, even there is no center. Another approach how you would explain the concept is more, I must say it's a retrospective analysis in a way, but you would say what we try to do is to make a very tight or compact building. The idea to have as much space as possible with as little surface as necessary, in spite of saving energy. So the ideal would be to build a sphere, but as you might know, to build a sphere, in fact, is rather difficult or challenging. So this ideal concept was kind of distracted, and we had to although we had a certain amount of parameters, inner and outer parameters that led to a certain distraction of this ideal form. For example, the photovoltaic I mentioned before, which is an important piece or part of this whole concept and should be integrated into the building. So we had to cut the facade to integrate this huge surface at this very specific angle. Or rather simple things, to have a roof that gets rid of the snow loads and so on. So very simple but very precise operations that led to the final shape or geometry of the building. And then another important idea is that how you organize this building spatially or structurally. There we came up with the idea that we organize it completely like radially. That means we organize the floor plan into segments, like 10 segments, each floor stacked up 5 times, and then we ended up with this like kind of cellular system with 50 quite equal cells. And this system is our like structural system, but it's also our spatial system. So this is like the main concept of the spatial and structural organization of the building. Another important concept is about the circulation, the vertical access to the building. You might expect in such a building which is organized in segments or radially organized, you might expect the vertical circulation in the very center of the building. But as our project is quite tight, and somehow it was too tight we had no space in the center. So what happens, we shifted the circulation to the facade, which might be surprising because usually the facade is necessary to provide light and air to the rooms. But we kind of turned it around and put the circulation to the facade and gave it light and air. So this system starts here in the basement and goes up to the 3rd floor, and doing this, it's a cascading stair system. Doing this, we rotate around the axis like a 360-degree rotation. And important, this circulation space, it's not only a vertical access, but it's also our like emergency exit, and it is also our like a ventilation duct. So it's a kind of low-tech thought that the ventilation goes through this like circulation space to the rooms, but it also is it's accompanied by a ribbon window, like a spiral window that allows us to gain some passive solar energy. And last but not least, it gives the visitor a nice view to the landscape. So this actually is a section through this orange actually, but now it's becoming a building. And this orange, you see, actually the projection is kind of, it's not very nice, it's too wide. You have to imagine it a little more narrow. But this orange now sits on this foundation here, So here's the rock. We blasted out one story step out of this rock, and then we established this foundation structure, like a steel structure, and on top of this steel structure, we put this pure 5-story timber construction. And here you have a floor plan of the foundation situation, quite, I mean, underneath the building, where you see how we sit or how we put structure on the ground. We try to touch the ground as little as possible, in spite of having like outside air underneath the building, so it's ventilated around this timber construction. You see the 10 axes, which are the main structural elements and also spatial elements, and the center foundation and the small foundations at the periphery. And here in this small room at the very bottom of the building, there's this wastewater plant. Now, if we have a look at the building services at this level, here you would find stuffed, like in an airplane, very tight space, you would find this small wastewater plant, and here you will find the thermal collectors, and here you find the freshwater pipes coming from the rock cavern. Going now into the building, into the timber construction, into the warm shell of the building, we enter here. We get rid of the skis, we change shoes and come to the first landing of this first flight of stairs here. In this area there's quite some space for technical issues and storage space for the warden and his staff. Now we change to building services again. What I explained before, those schematic drawings now become physical. They need some space and they need to be organized. And here you see all those elements like the storage, the heat storage, ventilation system, backup supply, battery, and so on. So you see it shifted away from this shelter towards like quite a heavy instrumented building. We go up, we come up this stair, and now we come to the ground floor, which is connected to the facade, to the terrace in the south, where you have like access to the dining room, or here you have a second like entrance situation. You would enter here reception, and then come to the guest room, the kitchen in this area, and here we have a second vertical circulation, which is for the warden and his staff, which connects the kitchen and the storage below, as well as his small apartment in the first floor. So it's like a hidden, like a second circulation system. And here you can see the start of this ribbon window as I was talking about. So this window starts here at the kitchen, goes over, follows the dining room, and here it changes the room. Now it follows the circulation, the staircase. Coming up to the first floor, another landing, and now the guest goes into the center of the building, and here you would get access to the first guest rooms, as well to the bathroom and toilets. This seems to be rather normal to have bathroom, toilets, and so on, but in behind you have to think there's quite some technological effort to provide these elements under these extreme conditions. And here's the small apartment for the warden. And now we go up to the second floor, and what you realize, so that the system rotates always like two segments. We started here, ground floor, first floor, second floor, and now coming up to the last third upper floor, which now is under influence of the south facade, which becomes spatially relevant. So it's not just it's a question of facade, but it also influences the geometry of the rooms in here. We have a look now at the building process and the construction of the building. Here's the building site in 2008 when we started to work. Here's the foundation going on, and here you will see the rock cavern, the reservoir, about 40 meters above the hut. Helicopter is something kind of unavoidable. Once you decide to build there, you have to deal with this issue, which means, first of all, it brings a lot of gray energy to your building, and second, it's a question of it's an economic question. It's quite expensive to work with a helicopter. That means every kilo we had to bring there cost about 1 Swiss franc, which is almost like €1. So this really expands the cost rather extreme. So this was a challenge for us to reduce weight wherever we could and to organize the logistic most efficiently as possible. And this was one of the very strong arguments also for the timber construction. Timber is not only a sustainable material as it grows, but it's also very it's a very cost-efficient and time-saving construction in terms you can prefabricate mostly everything, very precise, and it is very strong in terms of structural reason. So this is a very good material for us under these conditions. Here you see the building side of the reservoir, which is a nice space, but it will be filled up with about 240 cubic meters of water. That is good enough for about 1 year. Here you see the foundation work, or the steel structure, prefabricated down in the valley, pre-assembled to check measures, and then disassembled, brought on place, just put on the concrete foundation. And this is the building site after the first season. You have to imagine you have a very short period during summer when you can build there. So this is end of 2008. The foundation is ready to build up now this 5-story timber construction, which looks like this. This is like a plan of the beam construction. So we are missing like all flat elements. I mean, there's no indication of the cross-laminated timber that covers up the whole structure. But here you see nicely the two geometries we had to deal with. First, the geometry of the facade, which follows a certain set of rules, and the geometry of the inner structure, which is perfectly symmetrically built up. And these two geometries, they somehow collide or come together in rather complex situation. This is, with today's technology, it's quite easy to build, meaning we have fully computer-controlled manufacturing, so that what we plan three-dimensionally on computer goes straight to the computer-controlled fabrication, and we can produce such corner situation quite easily, even introducing like traditional wood-to-wood junctions, for example, here, so that you really can work nice with the wood, also kind of even in a very traditional way, but efficiently and economically. This is the main structural concept, which means that those every 5 stories and all those wall elements had to be kind of put together to create one big shear wall that takes, first of all vertical loads, but also the extreme horizontal loads, meaning wind up to 250 km per hour and earthquake. Translated into like forces, meaning that you have pressure and tension at the very extreme here of 400 kilonewton, which is like 40 tons pressure or tension, which is not a problem for a timber beam itself, but which is a problem how you connect one wall to the other, each story to each story, to create this big shear wall. Translated into construction, we kind of created like 3 different wall types, or which is, one of them is a typical framework boarded on both sides in the basement, just very thick and heavy walls here. Then we have an open structural timber in the ground floor, and then we have a kind of double wall system in the first to third floor. This double wall system is actually quite structurally it's the same as here, but what we did, we cut a typical framework construction, we cut it into 2 pieces and put it together back to back. So this looks like this. Here you have a section through this double wall system, which means you have this now visibly and spatially relevant. You see this framework situation, like horizontal and vertical members of the framework, then boarded on one side with a cross-laminated timber, and then another element put together back to back. And this was in spite of reducing weight, that each panel could be transported by a small helicopter first, and second, to give back the architecture this rather constructive expression of timber, that we show all like linear elements in the architecture. And here you see the junctions, which are like steel junctions from each floor to each story to the next, where we had to bend together this wall. Here you see second floor to first floor, and then the junction from first floor to ground floor, now changing to this single wall system, this structural timber system, then the junction down to the basement with this boarded framework here, and then the connection to the steel structure underneath. 3-dimensionally, it looks like this: the double wall system, the steel connection to the structural timber here, ground floor to basement, and the connection to the steel construction here. This is the horizontal, like the horizontal floor plan, where you can see how we had to divide up the elements, or each segment, into several pieces, that it in terms of dimensions and weight was transportable at all. The wood is all locally grown, fabricated, preconditioned, cut, drilled, and so on, computer controlled, all full automatic, and then kind of assembled, which is quite an easy work, because all the elements are precisely cut, and you just have to put them together like a puzzle. Control the conditions of your humidity is important, as you have very low humidity in the high Alps. So the condition is important to control, and here you see a stack of those elements, like around 420 elements ready for transportation. And here the building site in 2009 in spring, which means May, so several meters of snow still. We had to dig out the foundation and started up with the erection of the building. So each piece was put on a truck, was put on the train, another train, and then to the helicopter, and then straight to the building site, put right into place and fixed, and stacked up story for story. Here you get an impression about the heavy structure, or the rather extreme forces you have in the building. These are some of the steel connections in the structural timber in the ground floor. You see here, so it's not only timber, but it's timber and steel connectors. So this is unavoidable if you have such extreme forces. This is how it looks on site if you put it together with a certain ornament to kind of give some character to the beam. So it's not just a technical issue, but it's about space, it's about architecture. Here you get a nice view in the basement where you can see these access walls, the connections down to the steel structure underneath, the connection to the ground floor here. And here you get an impression of those double wall system. You see here the open framework shown on the room side, so it's part of the architecture of the expression, and put together back to back and see you 620 kilos, 650 kilograms. So this is has to deal with logistics, but it's also construction thinking. So this comes together. And this is the building, like the timber construction, which is a pure timber construction without isolation first. So the idea was to erect this structure, and then that we really could control and seal every joint of this puzzle, and then cover it up with a thick coat of insulation and protect it with a very thin aluminum skin, the photovoltaic kind of glass facade, and the ribbon window starting here, kitchen, dining room, following the staircase. And here again the construction, you see the timber construction underneath covered up with 30 centimeters of insulation, ventilation, and then a very thin aluminum skin, or in this case photovoltaic facade. In horizontal section, you see the interplay between, for example, this small window, which sits perfectly in between those vertical beams, and horizontal vertical section, how the small window fits to the bed. And this another interesting element, the ribbon window, which is a complete different construction. It's a aluminum post and beam construction, also prefabricated, and interesting for us because this thing goes around the body like a tattoo, so it's like a snake, and somehow it had to fit on site. And this was surprising how precise you can work either in metal construction but also in timber construction. And here you see in horizontal section, you see the relation between today's like 3-layer glazing towards a thick insulation package of 30 and another 15 centimeters. So these are extremes in both ways. How we fit in this ribbon window into the structure. This ribbon window had to pass specific like fire proofment. And then in the interior, we had to cover up in the circulation space, so in this staircase, we had to cover up the timber with plasterboard, as it is our like main fire exit. Then once again, building service is not just a schematic drawing, it becomes physical, and it has to be organized, electricity, ventilation, heat storage. And here, the main, like, quite kind of natural resources we have to deal with: heat and power, electricity. And this is the result. At the end of 2009, the building here, it shows that there's a lot of thinking about it, but in the end, it's just a very, very small, tiny bit in this rather tremendous landscape. So, and this was, for us, interesting to deal with these extreme conditions, extreme in terms of the density of the project on one hand, and the extreme landscape that surrounds it. And here